Good morning, everyone. So my name is Leonardo Marmol, and today I'm going to be talking about KeyValue Stores and Flash. This is work that has been done in collaboration with Swaminathan, Sundararaman, and Nisha Talagala, both from SanDisk, as well as my advisor, Raju Rangaswami, from Florida International University. So first, let me start by talking a little bit about KeyValue Stores and what they are. Basically, KeyValue Stores have become the preferred data management solution for many internet services. And the reason for this is that because they provide fairly straightforward and simple interface that allows you to, through the get, put, and delete, to operate on your data. And when compared to relational database systems, they provide a weak inconsistency model. And the main motivation for this is because they're basically trading off performance and consistency. Now, some of the limitations of existing KeyValue stores that are tailored to Flash have to do with the fact that all of them provide they use some mechanism of log structure of out of place updates. And this is because the physical characteristic of SSDs that forces you to write out of place. In addition, that typically people assume that you get better performance when you use sequential writes. And this is true for hard disks and older SSDs. Now, once you do this out-of-date update, you're also forced to have some form of compaction or garbage collection mechanism that allows you to reclaim the space that is no longer used, basically all copies of your data. And a direct consequence of this is that you're basically adding write amplification at the application level, which of course has some performance penalty, as well as reduce the lifespan of the NAND flash. Now, even though this approach is very popular, the question is like, how bad is the situation? So to better understand this, we took a look at LevelDB, which is a KeyValue store from Google that provides a very interesting compaction mechanism. So the experiments that we see here is very simple. We basically use its own benchmark, and we set up, we said define the working set as 1 GB and 4 GB. Those are the clusters that you see on the left and the right. And we measure how much data it gets straight into the actual media. So we see that depending on whether the writes are sequential or random, synchronous or asynchronous, we see that the write amplification grows significantly, particularly with the case of the random writes and synchronous. So what we see in here is that the write amplification varies, but it can get as bad as 40x. So basically, you write 43x more data than what you intended. And to be fair, this is not a problem that is unique to LevelDB. It's basically a direct consequence of having this logging mechanism on top of the already existing log on the FTL. If you want to learn more about it, I encourage you to read this paper called Don't Start Your Log on My Log, which describes this phenomenon in more detail. Now, if we look at the design of existing KeyValue stores, we find typically something like this. We have an application that interacts with the KeyValue store, and this KeyValue store usually provides some logging mechanism so that you know you're always writing out of place and taking advantage of the sequential write. And by doing so, you also require some data mapping techniques so that allows you to know where your data is. And also, of course, you have to have some compaction or garbage collection technique that allows you to reclaim space that is no longer used. But if we take a look also at the FTL, which is the software layer that basically makes the flash look like a block device, we see that some of this is also already in the FTL. The FTL provides, of course, a standard read-write interface as long as trim. And you see here from this diagram that as well as the KeyValue store, it also provides logging, data mapping, and garbage collection, as well as other things. So what is the problem with this? Well, clearly there's a lot of redundancy. So how can we improve the situation? Of course, the first step would be to export some of these techniques and infrastructure that is already in place in the FTL. And the way of doing that is by simply modifying the interface that the FTL exports from the traditional interface that only allows for reads and writes to an extent the one that allows tap into the infrastructure that is already in place. Now, because we were talking about specifically of a KeyValue store, we also wanted to change the data mapping to make it to making it sparse. And what I mean by this is typically, you can think of it as the way the memory is virtualized. That you have typically a couple of gigabytes of memory, which gets virtualized, and then the application sits in the process address space. much more memory than what really exists. So that's basically what we're doing here. We're virtualizing the actual storage so that the logical addresses are much more, there's a huge range in comparison to the actual capacity of the device. So by doing so, we can basically reduce and simplify the key-value store into a simple hashing scheme, which makes the design of the key-value store a lot simpler and smaller, gets the application closer to the FTL, and experience a much better performance. So to get some details about how we do this, is our key-value store, the high-level architecture looks something like this. So it's a user space library. It's written in C/C++. The applications can interact with it through the typical API, which provides the typical interface like gets, puts, and deletes, as well as many others. And our key-value store talks directly to the block device. So we don't have a file system in between. And the main motivation for this is to get better performance, reduce the overhead. But of course, we're also taking into charge the task of managing this block device. And we're also assuming that the FTL provides a set of primitives that, besides the existing read and write and string, has some extended interface that allows to do things like write atomically and check for the existence of a mapping. We'll see more details about it in a moment. Now, the API of our key-value store provides what you will expect. It allows you to open and create key-value store, or close and destroy it, basic operations like get, put, and delete, and bash operations. So here I have a small code fragment that allows you to see how you will use it from your application. So you typically open the device, followed by creating or opening the key-value store. And then at that point, you have everything that you need to do puts and gets. And of course, check if a specific key-value store exists in your key-value store. So the interesting, of course, this is just a subset of the APIs. And an interesting point here is that every of these operations is done atomically. So that we provide an interface that is not typical of key-value stores, but it allows applications to do an update of multiple key-value stores atomically. And we get this basically for free because it's already part of the functionality of the FTL. If you want to learn a little bit more about how this is implemented, there's this interesting paper called Beyond Block I/O, Rethinking the Additional Storage Primitive, that gives you more intuition about how this is accomplished. Now, how do we perform IOs in this sparse address? So basically, the sparse address is divided into a virtual slot of the same size. And of course, this could be configured at the creation time. So basically, when you have some data, it looks something like this. You have all these blocks, and the one with colors is a portion of the virtual block that is used. And the FTL is in charge of creating this mapping between logical addresses and the actual storage. So if we were to insert a new key value pair, say this one, basically what we do is just hashing the key, and we obtain a logical address. And then followed by that, we basically ask the FTL, do you have anything in this virtual block? If the answer is no, we issue a write to that address, in which we write both the key and the value, and the FTL is in charge of making the mapping. A couple of interesting things here is that the exist operation doesn't require any I/O, so it's an in-memory operation, therefore it's very fast and has very low latency. And in the event that the LVA that we computed already have an existing map there, we basically use polynomial probing to rehash and get a new slot. Typically, this doesn't happen very often because the sparse address is very large, so the probability of getting an empty slot is very high. Now, one of the problems with this design so far is the fact that since we're not using, for instance, since we're not running on top of a file system, there's not a straightforward way to creating multiple key-value stores on the same media. So, of course, one possible solution for this will be to create multiple partitions, but as you will know, the solution doesn't really scale. So what we propose is something called pools. And the way you can think about that is you can think of a pool as a unique set of unique key-value pairs that share the same pool ID. So it looks something like a diagram that we have on the right, in which you have a couple of pools, and the one highlighted in red is the one that is shared. Notice that they have the same key, but they are in different pools, so these are completely different keys. So this gives you an illusion of creating multiple key-value stores that different applications can use on the same media. So basically, the way we accomplish this is by redefining or modifying our hashing scheme in which now. So now instead of taking just the key, we also take the pool ID to compute the LBA. And by doing so, we require no extra memory for the metadata. But one of the key problems that we have that we want to solve is that we want to do this in a way that doesn't increase the number of IOs that is performed in average per operation. So far, we have basically 1 IO per operation. And of course, by introducing this notion of pools, now key value pairs are uniquely identified by both its key and its pool. So how does it work if we were to insert a key using pools? So basically here we have a similar diagram. So when we want to insert a new key value store, a new key value pair, as before we hash, but now using both the key and the pool ID. We check if there's something there, and now we write. But notice that now, as opposed to, instead of writing the key value pair at the offset 0 of the virtual slot, we're writing an offset. And this offset could be 0 or bigger than 0. And what it's basically telling us is that what's the pool that this key value pair belongs to. And this allows to basically have no extra metadata and very effectively and efficiently determine whether this key value pair belongs to one pool or another. And of course, once we define the offset, we basically write it and everything remains the same. A couple of notes here is like, as before, we still have to guarantee that every virtual slot contains only one key value pair. And as I mentioned, the offset is the one that determines the pool ID. And of course, this adding this offset in the virtual slot does not translate into wasted space in the flash. And this is, of course, guaranteed by the FTL. So in addition to this, we also have, we implement caching. So we have the traditional read cache that allows to improve the read performance. So this cache is not involved with writes. Basically, when you want to read, if it's a popular key value pair, you read it off memory as opposed to going all the way to the media, issuing IOs. But we also have the notion of a collision cache. So in KeyValue stores, once you want to fetch some data, you have to read and compare to make sure that this key value pair is the one that you want, in fact. And the reason for this is because hashing, even though it's very effective, it's not perfect. So you want to make sure that you're getting the data that you want. So in those extreme cases, you basically have, there's a possibility that you issue more than one IO to obtain the data that you want. So what collision cache does is basically store a little bit of metadata for these cases so that the next time you ask for it, you don't have to do multiple IOs. And because these events are very rare, a very small amount of cache is very effective for the collision cache. If you want to read more details about this, I encourage you to look at the paper. Now, let's take a look at some of the performance numbers that we have here. So the first one would be about pools and how they scale. So what we have here is a graph that measures throughput as a function of the number of pools. So what we want to do here is see, having set the size of the working load, we increase the number of pools and see how the performance changes as the number of pools increases. And we're comparing this with LevelDB. Of course, LevelDB doesn't have a notion of pools. So what we did was basically compare, if we have 2 pools, we run 2 instances of LevelDB and see the performance. So let's start by comparing the write. So the blue line is the write performance of our key value store. And the one that we mentioned here that you can barely see, believe me, there's a line there, is the writes for LevelDB that are synchronous. The performance is so bad that it's basically out of the picture. So let's compare it with your writes of LevelDB that are actually asynchronous. And we see that even though LevelDB's performance writes asynchronous that have been buffered by the file system cache, we still outperform LevelDB by a significant margin. And this is really interesting because typically people think that writing sequentially and give you better performance, but in our case, because we hash, every write for us is both random and asynchronous, and still we're doing much better than LevelDB that is taking advantage of the cache of the file system. Now here we have the same experiment, but now measuring the throughput of reads. And what's interesting is, again, of course, the blue line is our KeyValue store, the red line is LevelDB. So we see here that about for up to, let's say, 32 pools or 32 LevelDB instances, the performance of our reads is to some extent comparable to that of LevelDB. But what makes this really interesting is the fact that this is the best possible case for LevelDB. The reason for that is that LevelDB is both benefiting from its own cache and the cache of the file system, and it's a cache that is having warmed by the previous experiment. So we run this read workload right after the write workload, so all caches are warm. And still, LevelDB and our KeyValue Store number time memory KV, even without using any caching, we're still able to keep up, even though every single read have to go to the media, and most of the reads that are being served by LevelDB are being read off the cache, both file system and its own cache. So we also use ycsb to provide for performance, and we have here two of the tests that it provides the workloads. So we have the read-only one and the heavy one that provides a mix of reads and writes 50% each. And what we're looking at here is a performance of throughput as a function of the size of the read cache. So we see, as before, that the red line is for LevelDB, and we see two lines for our KeyValue Store, a green one and a blue one. The green one represents that of the performance when you have no use of caching of the collision cache, and the blue line when you have 64 megabytes of collision cache. In both cases, we see that the performance of our KeyValue Store exceeds that of LevelDB by a significant margin. So, in conclusion, what we want to say is that the typical intuition of writing in place and having applications that are optimized for KeyValue Stores, for Flash, applications that are optimized for Flash, it's not really what we think it is. It's much more effective to have an application that, as supposed to be optimized for Flash, is optimized for FTL, that cooperates with the FTL. And by doing so, that allows us to create a KeyValue Store that is very simple in design and implementation, that requires a constant amount of metadata independent of how many key value pairs you have. We were allowed to create multiple key value stores sharing the same flash, provide high performance and parallelism, and we benefit from the nice properties that offers the flash, like atomicity, durability, and very low write amplification, which compared to LevelDB in the worst case, we reduce the write amplification by a factor of 29x. Having said that, I'm happy to take any questions. Thank you.
From Alibaba. So if I understand correctly, so basically you try to hash the key to some integer as offset and then write to the flash device.
Yes.
If that's the case, I wonder if you could support, say, sequential query. Say, scan the keys in the sequential order as it's originally meaning, or you can do a range query. Right.
In our case, because we hash everything, there's no notion of order anymore. We basically gave up that. So basically, there's no way to have a range query or a sequential query.
Right. The follow-up question is there a way to extend your scheme, because you do see the analogy of all those logging and the compaction, garbage collection in the flash layer and the user layer. But is there also a way, think of other ways to kind of reuse that logic, but also supports the range query?
Right. It would be interesting to provide a solution for that. At the moment, we don't have a solution for that. The best we have is basically the notion of pools that allows you to somehow group key value pairs that mean something to you and then just iterate through those, as opposed to iterate through the entire space.
Okay, thank you.
Jeff Kenning, Harvey-Mudd College. So this, excuse me, this depends on an extended API in the FTL.
Yes.
So can we expect SanDisk to be releasing SSDs with a very nice extended API and finally give us access to some of those things inside their stuff?
I'm afraid I'm not the right person to answer that question, but maybe Swami can. one thing that is probably worth mentioning is that even though all this work has been done and is specifically to the SSD that for SanDisk, there is nothing conceptually that is stopping other SSD manufacturers from doing the same thing. We're basically saying you should export this interface so the application can benefit from it. And of course, for instance, the case of the sparse address space, you can think that only we care about that because we're a KeyValue store, but there are many other applications for that. For instance, if you were to do caching, you could probably benefit from this as well. And there's a solution that SanDisk provides that uses this as well. And also a file system called DirectFS that also uses and benefits from having a sparse address and all this extended interface. So it's just basically another example say, hey, extending this interface makes sense. We should all do it and take advantage of it.
Two related questions about modifying the values, modifying a key. If someone writes a key value pair and then says, I want to change that key to be associated to a new value, you're writing it to the same location as before, right? Or is that even something that you...
Well, you write it the same logical location.
The same logical location.
Yes.
So do you have atomicity then of the modification? I wasn't clear on that.
Yes. We didn't have to do anything special for having these atomicity properties. Of course, the FTL writes in this logging fashion.
Right.
So you can think that it's not a quantum leap making this log and providing atomic, right? So we took advantage of that, and basically every operation that we perform is atomic. So even the bash operation, which is typically not a type of semantics that is typical of KeyValue stores, but applications can take advantage of that and write atomically a set of key-value pairs, which is very nice because then it's a lot simpler from the application perspective to accomplish consistency, right? You can write a vector of key-value pairs atomically.
Okay, so if a second question is, when you're doing that sort of modification,
which modification are you talking?
When you're modifying the value at a given key.
Also updating a key.
You're updating
okay.
the key. Doesn't that cause write amplification on the SSD side? And it seems to me like long sequential writes create a lot of write amplification at the system side and very little write amplification in the SSD, and you've kind of just flopped where the write amplification happens.
Well, perhaps what I mean by write amplification is the write amplification generated at the user space, generated by the application itself.
Right.
Of course, there's write amplification that is generated by, for instance, the garbage collector or things like that. There's not much we can do about it, right? But what we can do is reduce the write amplification generated at the user space. In the case of LevelDB, what happens is that it uses these compaction techniques that move data from one level to the next. So basically, the same data is moved multiple times, which generates a lot of write amplification. So the data that is written to the storage is much more than what you initially intended. And that's what we want to reduce. And one way to do this very effectively is by basically exporting this extended interface that you no longer need to have this mapping or moving data around.
Right.
You can simply hash and write to the address. And basically, the FTL does everything else for you. And it's not doing much more than it was doing initially. You still, the FTL have to do logging, you have to have mapping. We're just basically taking advantage of that by extending the interface that it exports.
But you're now invalidating small chunks out of large blocks, and so every time you update a key,
yes,
you've invalidated part of one of the blocks inside the SSD.
Yes.
So the SSD has to do eventually a garbage collection cleaning algorithm.
Yes.
Very parallel to what you were doing up at the user level.
Can we take that offline?
Okay.
We're
Fair
running
enough.
out of time. All right. So yeah, sorry, we're running out of time. All right. Thank you.
Thank you very much.